Okay, so PS7 is coming due the next few days, and then PS8 will be out and due after spring break. Any questions or problems? Yes?
So I'm a bit curious how the late days will work for PS7 since it's a bit different this time.
Okay. So actually, if you look at I spelled out the late days.
Oh, okay.
So like if you look at, let's say, PS4 here, I'm not sure how it shows up for you. But if I go back to here, it's due the 6th, which is Friday, until the 8th.
Okay.
So basically, the things that I may do Friday, that are normally do Thursday, still have 2 days of late day. Do you have a question?
Yeah, could you just go over like what PS3 is asking? Because I don't think I quite understand that.
7.3? Right there. Okay, so let's see. I'll just write here. So you've got you want to calculate this A to the B to the C. Okay, and that's important. It's not A to the B to the C, which is a different animal. This is A raised to that massive exponent mod n, and you know that A. What do you know about A k minus 1? I've already forgotten. All right. Okay, that's the multiplicative inverse of A if you're working mod n. All right, that's the setup. And you're supposed to find a way to do this calculation in n cubed time. You want to do it in O of n cubed time, where n is little n is the length of big N, length of all these numbers. Okay? And you know, your usual trick of simplifying the base of the exponent with the modulus doesn't, you can there's no point in taking A mod n because A is already less than n. But there's no way you can even calculate B to the C in O of n cubed time. So the trick is to find a way to simplify that exponent right there. Make it so you can calculate A to that power by calculating A to a much smaller power. So you need to use this assumption to modify that so that the A is the same as the exponent small. And I'll just remind you that since A to the k minus 1 is the inverse of A, what's A to the k? All right, A to the k is 1 mod n. That's the first step. So take that A to the k is the same as 1 and use that to simplify things. Does that help? Any other questions? Okay. One. So I want to remind you of a fact about RSA before we go forward. It can be used in 2 modes. I mentioned this last time. So you can take the message you're trying to encrypt, the number you're trying to encrypt. Then you can, typically if you're trying to transmit a secret message, you encrypt using the receiver's public key. So if you're trying to send to Bob, you need Bob's public key. Bob needs to give you his public key. You encrypt the message with Bob's public key and then send it to Bob. Anyone can intercept the message, but presumably Bob is the only one who knows his secret key unless he shared it. And so only he can decrypt it without massive effort, as far as we know. Okay? So that's the standard way to do encryption with RSA. But you can turn it around you can encrypt and decrypt with either the secret key or the public key. So another thing you can do is take a message, encrypt it with a secret key, and then later decrypt it with the public key. And that's not really for keeping secrets, because if Bob were to take something and encrypt it, run the encryption algorithm using his secret key, and then send it out, anyone could read it, right? Anyone knows his public key, anyone can decrypt it. But the point of that was, what was the point of doing it that way? Why would Bob do that? Yeah.
Authentication.
Right, authentication. The idea that you say it's some contract, and Bob encrypts it with his private key, and then posts it on the internet. Now, anyone can look at it, and the fact that they can decrypt it with his public key means that it must have been encrypted with his secret key, which only he knows. So that's a form of proof. It's called a digital signature. It's one kind of a digital signature. It's proof that Bob originally encrypted it with the secret key. It traces it back to Bob. So we're going to make use of that fact shortly. Any questions I could answer about that before I go any further? Turns out to be an important point of e-commerce. Because in e-commerce, we're going to use both encryption and signing. Okay, so here we are. So here's our scenario. We have A, which you think of as Amazon, B, you can think of as the browser. And the browser wants to buy something from Amazon. So here's the first crack at something we might try. Browser generates an AES key, so a symmetric block cipher key, sends it over the network to Amazon. Amazon says, okay, during this session, we'll use this key, encrypts some message M1 and sends it to the browser. The browser can read it because the browser knows the key, and vice versa. So they can talk back and forth using that key. And we talked about what's wrong with this. So remind me, what's bad about this scenario? Why isn't this the way things really work? Yeah?
Someone who can intercept the traffic runs the key so they can encrypt all the messages.
Right. Someone can be sitting in the middle and intercept the key and read everything that goes by. And these forms of attack are called the man-in-the-middle attack, where there's someone that you don't know that's essentially intercepting everything going back and forth. Now, in this case, it'll be the woman in the middle attack because E is Eve, the eavesdropper. So just to nail this down, Bob sends Kay the key to Amazon, thinks he's sending it to Amazon, but actually he's sending it to Eve. Eve intercepts it. Eve makes note of the key and sends it on to Amazon. So neither Bob nor Amazon is to the wiser. The message got through like both expected. But Eve holds the key now. And now when the message comes back, encrypted message, Eve can decrypt it. And of course, Eve doesn't want to tip off Bob that she's reading the message, so she just sends the message along to Bob. So Bob gets an encrypted message back, just like he expected. And it works the other way too. So Eve's reading everything that goes back and forth. So that's the key transmission problem. And so let's try to fix that. So now what we're going to do is we're going to combine AES, the symmetric block cipher, with RSA, public key block cipher. So what Amazon is going to do is send its public key. So piece of A is Amazon's public key. So Amazon sends its public key to the browser. Now what's the browser going to do with that public key? Remember, we're using RSA simply to solve the key transmission problem. Mm-hmm. Right, so it'll generate that key like before, but instead of sending the key back in plain text, it'll encrypt it with the public key. Send that to Amazon. Now, Amazon is able to decrypt it because Amazon knows its secret key. Now both sides have agreed on that K, and now communications can go as before. What happens if someone intercepts piece of A of K? What if Eve intercepts that encrypted key? Is that a problem now? Yeah.
She doesn't know Amazon's secret key, so she can't decrypt it.
Right. She doesn't know Amazon's secret key, so yeah, we know she can intercept it, but she can't do anything with it. She can't decrypt it. Right? Now, what if she intercepts the public key as it goes by? Well, it's a public key after all, so you might wonder what's the difference. But in fact, that's a vulnerability. So let me show you. Let's put Eve in the middle. So Eve intercepts Amazon's public key. Now, it doesn't do Eve any good to just remember that public key because she can't really do anything interesting with it. But what she can do is send along her public key. You know, Bob doesn't know, it's just a bunch of bits. He doesn't know that he's got Eve's public key as opposed to Amazon's public key. So what's Bob going to do now? Bob got a public key just like he expected. So what's his next step in the protocol?
Encrypt using that public key.
Right, encrypt using the public key, encrypt K using the public, what he thinks is Amazon's public key, but which turns out to be Eve's public key, and encrypts it. Eve intercepts. What's she going to do? She'll decrypt it with her private key, her secret key, and now she knows K. What will she send along to Amazon? She'll re-encrypt it with Amazon's public key, because that's what Amazon's expecting. So both sides of the communication, A and B, it looks the same as before. Bob gets a public key, encrypts K, and sends it, and Amazon's expecting to get back a key K encrypted with Amazon's public key, and that's exactly what it gets back. But Eve is sitting in the middle, and Eve knows K now. And so now when the communication goes, Eve's able to read it. So the fundamental problem is public keys don't come labeled with whose key they are. Bob has no way of knowing in this scenario that he's actually dealing with Eve's public key as opposed to Amazon's public key. Yeah?
The key is public to begin with, though, so couldn't Bob go look up at some like third-party source to see if the keys match?
Okay. So one solution would be instead of Bob relying on Amazon to send the key, to go to some trusted third party and look it up, verify that it's really that public key. And in fact, that's close to what happens. There has to be, you have to do better than just ask the Amazon for their public key, because this might happen. But what is done is, see, there are lots of public keys out in the world. And so having a place where you can look up every public key in the world, first of all, you'd have to make sure that site didn't get hacked. So there's a different solution that's done. But first of all, are there any questions about why this is bad? Okay, so the solution that's used involves signing. So far we've just used the ability to encrypt using public keys. Let's do signing now. So this is what we're going to do. What Amazon sends to Bob in the first request is what's called a certificate. And the certificate contains Amazon's public key and information about Amazon, such as its IP address, the expiration date of the key, various other information. So identifying information that says, this is my public key, I am Amazon. And that certificate is encrypted using a trusted third party's secret key. So there are companies that are in the business of signing certificates. They're trusted third parties. So VeriSign, for example, is a prominent example. So if Amazon wants to do e-commerce, Amazon generates a public-private key pair and then negotiates with VeriSign to say, okay, I'm Amazon, this is my public key, here's $10,000 or whatever, I don't know how much it costs, but that's VeriSign's business model. You pay VeriSign. I'd like a key with, that's good for, a certificate that's good for 24 months. And VeriSign takes its very closely held secret key and encrypts Amazon's certificate with it. Okay? Now, what happens when Bob receives the signed certificate, signed using VeriSign's secret key? Yeah? Right. It's been encrypted using VeriSign's secret key. So VeriSign is this trusted third party. We're going to assume that everyone knows VeriSign's public key. I'll explain how everyone knows it shortly. And so decrypts it using VeriSign's widely known public key. And now Bob knows, is assured that this thing is legitimate, as long as you trust VeriSign. And then things proceed as before. We know, so now Bob just didn't just receive Amazon's public key, it received other information verifying that, yeah, this came from Amazon, so it's labeled as whose key it is, and it's signed by a trusted third party. Now, could Eve intercept this thing here? Okay, could she read the certificate? Yeah, she could read the certificate. Could she substitute, could she then fake it out? Could she then sign it with her secret key and send it along? Okay, and what's the problem? Why not? She could certainly send it along, but why wouldn't that fool Bob in this case? Yeah.
Because you wouldn't know Eve's secret, or sorry, public key,
Well, she might,
or you wouldn't be decrypting.
right. Bob is expecting that, he knows this thing has been signed by VeriSign. Somehow, that detail's not included in here. But Bob's expecting to get a certificate signed by VeriSign. If he gets one signed by Eve, he'll know it's fake. If you can't read it with VeriSign's public key, then he knows it's been faked. So Eve is foiled in that case. So we decrypt and proceed as before. Now we know we've got Amazon's public key, and then we encrypt and send it over. Eve can't do anything with that either. And it works as before. Now, what's the vulnerability in this? What's one of the details that I sort of punted on here? So that I'd explain later. Yeah.
Getting B to know what VeriSign's key is.
Right. How does B know VeriSign's public key? Well, what about this idea? What B does is it just contacts VeriSign's server and says, what's your public key? Is that going to work? No, because if Eve intercepted that, she could send back her public key and fool the browser and then start faking the certificate. Yep.
A list of certificates and verifiable third parties of the browser.
Okay. So the answer is they're called root certificates. These trusted certificates are built into your browser. So when you download Firefox, you download Chrome, you download Edge, built into the browser are these third parties public keys essentially. Yeah.
How do those get updated?
Well, that's a good question. How do they get updated? So yeah, or we can make it even simpler. When you download the browser, how do you know you're downloading a legitimate browser as opposed to one Eve is hacked up to contain, it's a working version of Chrome, and the only difference is she substituted her public key for VeriSign's public key when you download it. So how do you know you got the right one? Yeah?
I guess an MD5 hash.
Okay, when you go to the download page, there's typically a hash of the software, of the binary, and after you download it, you can hash it and see if it matches. But Eve could mess with that too, couldn't she? If she can hack the browser and get it on the download page for Chrome, surely she could replace the hash on the download page with the hash she computed. So the answer is there is no absolute certainty that you got the right thing. At some level, you've got to trust or hope for the best or something. The idea is just to make it really hard for something like this to happen. Yeah.
If memory serves, I'm pretty sure some of these root certificate hacks have been performed before, and like fake software has been signed supposedly from Google in the past. So there's
Okay, so this hack has happened. Yeah. So, yeah. Now, how do these certificates get into the browsers? So VeriSign, people are paying VeriSign to sign their keys. Are the browser providers, are they like a public charity that, I'm not certain, but I'm sure that they're being paid to VeriSign must be paying them to put their root certificate in. And I remember there was a case a few years ago where there was some shady company that got their, I don't know if it's related to your example or not, but it was sort of a shady third party managed to get their certificate in. But it later came out. So anyway, this isn't the full detail of the protocol, of course. It's just the basic idea of how it works. But what I wanted you to see is a couple things. One is the interaction, that we're not using just RSA, and we're not using just AES. What's the reason we don't just use AES? Yeah.
We have the key.
Right, key transmission problem. Why don't we just use pure RSA? Yeah.
It's too inefficient.
It's too inefficient. So for credit cards, it wouldn't be a big deal. But if you're like trying to encrypt a streaming movie, that encubed algorithm is too expensive. So we combine the two. And then the other thing is to see that in this protocol, we're using both encryption and signing, digital signatures and encryption through RSA to make this whole thing work. One thing that fascinates me is when RSNA invented RSA, it really had no application. It was 1977. There was no web. No one was buying anything over the internet. I mean, it could be used to encrypt stuff that spies could encrypt, or you could keep things secret with it. But it didn't have anywhere near the application it has today. So it was sort of another example of a solution in search of a problem. But it came 25 years later. Okay, so that finishes our story about encryption and number theory. Any last questions I could help you with before we move on to our next topic? Oh, I guess I do have one more slide. This is just an example certificate. I went to my browser at some point. It's been a while because this certificate expired in 2016. But you can go into your browser and look at your root certificates. So this one was created, this is VeriSign's root certificate. There's a serial number. Down here are some hashes. There's the actual modulus, and this is the actual, the public exponent. So the public exponent is supposed to be a small integer. In their case, they don't use truly tiny integers. They don't use 2-bit integers. They use, 16-bit integers. Okay. Okay, we're moving to a chapter about greedy algorithms. We're going to study greedy algorithms for a while, now and after spring break. And this is an example of a greedy algorithm. Suppose you're given a list of meetings you want to schedule. So the idea is these white lines represent meetings. So think of this black line down here as maybe a timeline for a single room. So we've got some meeting room that's available from 9 to 5. And we want to schedule, we've got these meetings to schedule into it. So maybe this meeting runs from 10 to 11:30, and this meeting runs from 9:30 to 10:30, and so on. And obviously you can't schedule them all because you only have one meeting in the room at a time. You want to, your goal is to schedule the most meetings possible. Okay? There are other goals possible. You could say, I want to keep the room busy as much as possible. Or I want to accommodate the most people during the day. But in our case, we want to schedule the most meetings that we can. So what is the answer? What's the most meetings you can schedule in this instance? Yeah, there's a way to schedule 4 meetings. So those 4 I've highlighted there can be scheduled simultaneously. Okay, sort of flashed the answer there, but how can you, what would be an algorithm for doing this? Yeah.
So maybe pick the smallest one first and then the next smallest one.
Okay, so maybe pick the shortest meeting.
Yeah.
and schedule it. What do you think of that?
I would say you take the first ending time, and then after that, you take the next ending time. That's the
Okay, so we have one suggestion to schedule the shortest duration first and then look for the next longest that works and so on. Second suggestion was to schedule, first find the meeting that ends the soonest, schedule it, and then proceed. Any other ideas? Yeah.
I think with his solution, you also have to add in an extra conditional that to schedule the next meeting, you have to make sure that it starts after that first one. 'Cause
Okay. Okay. I think that's right as well. So I'm going to step back a bit. These are all examples of what are called greedy choices. So the problems we're going to study are called optimization problems, in that you're trying to optimize something. You're trying to find the best. In our case, the best schedule, according to some metric. And we're going to see all kinds of optimization problems between now and the end of the semester. Some, when we're lucky, we can solve with a greedy algorithm. A greedy algorithm, there's some way we can look at all the options. You've got a bunch of options, you've got to pick some. A greedy choice lets you go, this is my first choice. And you commit to it, and you reduce the size of the problem, and you make another greedy choice, and you continue until you're done. You never get stuck and have to back up and change your mind and go a different direction. So greedy algorithms are great when you can find them, because there's no searching involved. You've just got to be clever enough to come up with the right way to make the greedy choice. Okay? So let's go with the first suggestion. Would it work in general, it might work, not just in this case, but always, to pick the meeting with the shortest duration? Can you think of a set of meetings that would foil that? Yeah.
So now that I think about it, if you have two meetings that don't overlap and then like one small meeting that overlaps both of them, then that would give you just pick that one and then you can have the other two.
So you're saying something like this. We've got this meeting, and that meeting.
Yeah.
And the room is available in this time. So if we use that greedy choice, which says I'll start by picking the meeting with the shortest duration and then proceed from there, we would pick that short meeting, and we would not be able to schedule either other meeting because they all conflict. So the idea in a greedy algorithm is you make the greedy choice, and then based on that choice, you simplify the problem and then solve the simplified problem. So what is the simplified problem you have to choose, or you have to use? Let's say you pick this. How does that simplify the problem? What's the new problem you have to solve to find your final solution? Yeah.
Well, you can't schedule anything during that same time or before it anymore, so you have to look at everything after it.
Okay, so let's see, there's the eraser. So what I mean by simplification is, okay, you've scheduled that one meeting, so you're basically, the room is no longer available. So you've reduced the problem to one of scheduling meetings into the room that's available at these times. But what's another way in which you simplify the problem once you've committed to one choice? Are there some meetings you should throw away? Okay? What do we throw away?
Anything that overlaps with it.
Right, anything that overlaps with the meeting you scheduled. So I've got to get rid of that meeting, because we can't schedule it if we've committed to this one here. Whoops. And we get rid of that one. So at this point, there are no meetings left to schedule, and we're done. We didn't get the right answer, because the greedy choice strategy was wrong. But the idea is you make a choice, you simplify the problem. You get rid of conflicting meetings in this case, and you change the duration when the room is available, and then you continue. Now, it turns out that the second suggestion we have works out. So we repeatedly picked, see over here. You pick the meeting with the earliest ending time and discard all conflicting meetings and continue. So which meeting would we pick first? Which meeting has the earliest ending time? this guy right here. Now, is it all obvious? Is it obvious to all of you that this works? Because it's not obvious to me. It never has been. I believe it, but it is definitely not the thing that would have come to mind. It wouldn't have been my first choice for a greedy strategy. So we'll pick this and we'll eliminate all the conflicting meetings, those there, and then we repeat. All right. So what meeting do we grab next? This one here. So we commit to it. Get rid of conflicting meetings. We got this one now. We get rid of it. Get rid of conflicting meetings, and then we can schedule that, and we're done. Okay, so that's an example of this greedy algorithm in action. I want to point out a difference, the way the course is going to change now from where we've been going. We've been studying number theory. We've been studying graphs. We were studying specific algorithms, right? How do you do modular exponentiation? How do you find shortest paths in the graph? Now we're backing up. We're going to be studying algorithm design principles, strategies. So it's not like our main purpose here is to study the famous meeting scheduling problem. Our main purpose is to study greedy algorithms so that you can, design new greedy algorithms. That's the goal. And in fact, the caddis problem for next week is one where the problem is stated, and I'm telling you it's a greedy algorithm you need, and you guys got to figure out you got to do the creative part, which is design the greedy choice. Decide how to make the greedy choice. All right, here's some other ideas. Picking the shortest meeting first, and there's that counterexample. What about this? What if we said, no, pick the meeting with the earliest starting time first? Why bother, why earliest ending time? Why not earliest starting time? Can you think of a counterexample for that? Yeah.
You could have like a ton of really small meetings that all start after one enormous.
Okay. So, right, so I just did it with a few, but you get the idea. We got these two short meetings that we can schedule simultaneously, but this long meeting starts earlier. And so if we follow that greedy choice strategy, only the one long meeting gets scheduled. And again, you may think, well, that's better. We're making better use of the room because we're using it the entire time, but that's not our goal in this case. Our goal is to have as many meetings as possible. Okay, let's see another one. What about we process the meetings and we count how many other meetings each meeting conflicts with, and we favor we start with the meetings that have the fewest conflicts. That seems reasonable. So this doesn't work, it turns out. It's a little bit tough to come up with a counterexample. Yeah.
So the one that I think of is like a ton of really short meetings stacked up, and then a big long meeting, and then a ton of really short, and then big long, and then a ton of really short.
You've been looking at my slides?
No.
Okay. So something like this. It's hard to come up with, but it's even harder to describe to someone without a picture. So I've contrived, so I've got these 4 meetings I'd like to schedule, the 4 in a row right there. And I've arranged for these meetings that I like, they all conflict with 3 other meetings that I've put up there, just so they conflict with 3 other meetings. And then I've got this meeting right here conflicts with only 2. So the first meeting we would schedule would be this one, because it only has 2 conflicts. And after we schedule this meeting, we're only going to be able to schedule 2 others. So that's a fail. So this can be tricky to come up to. First of all, the problems don't come labeled saying use a greedy algorithm. So first you've got to think, okay, maybe there's a greedy algorithm, but you're not sure. Then you think, okay, assuming there is a greedy algorithm, what would be the greedy choice? But then you got this nagging fear that your choice is wrong. So you've somehow got to convince yourself that the choice will work in all cases. So it just takes practice to get after it. The fundamental idea behind greedy algorithms is pretty simple. Yeah?
Does latest start time work?
Would latest start time work? Yeah, that's like the sort of it's reversing everything. Yep, that works exactly the same way as the other one. Okay, So this is the standard way that we'll use to convince ourselves, at least most of the time, to convince ourselves that a greedy choice strategy is right. And the reasoning will go like this. We want to show that we want to argue in some sense that it's safe to make the greedy choice. That if we make the greedy choice, there is going to be an optimal solution that contains that greedy choice, that we're not backing ourselves into a corner. And the way we're going to do that is we're going to say to ourselves, okay, assume that there's an optimal solution that does not contain the greedy choice. So that's possible. There could be other solutions that are just as good that don't have the greedy choice. So our proof is going to consist of taking a solution that does not contain the greedy choice and showing that it can be manipulated, that the existence of that optimal solution implies that there's another optimal solution that does contain the greedy choice. So the existence of any solution that does not include the greedy choice implies the existence of a solution that does contain the greedy choice. That means that the greedy choice is always contained in some optimal solution. And so we can make the greedy choice secure in the knowledge that that's safe, that we can continue on and find an optimal solution. So let's try to apply that proof. Your next assignment will involve doing several arguments like this. So let's think about the problem. So let's we're trying to solve the problem, so we're going to let M be the meeting with the earliest ending time. There has to be at least one optimal solution, and often there are more. So let's call that optimal solution S, and we're going to assume that S does not contain M. If it does contain M, that's great, because that's what we want. We want there to be an optimal solution that contains the greedy choice. Okay, so let's assume it doesn't contain M. Now, one of the meetings in this set S, we'll call it M prime, has to be the one with the earliest ending time in that set. So we'll call that M prime. So I'm going to create a new set. I'm going to take this optimal solution that we found. I'm going to take out M prime, the one with the earliest ending time, and I'm going to replace it with M, our greedy choice. That gives us a solution S prime. Now, I claim that this is an optimal solution. S prime is an optimal solution. Let's think about that. First of all, is it, it's going to have to be the same length as S, right? Because S was optimal. Is it the same length as S? Yeah. You take S, you remove one thing, you put one thing back. It's going to be the same length. But what else do we have to say to convince ourselves of to argue that this is an optimal solution? Yeah?
So M prime has to have the earliest ending time from S, which means that M's ending time is either that time or earlier, because we know that's the earliest ending time.
Okay, so you're making the argument. So what he's trying to convince us all of is that not only is this the same length as an optimal solution, it has to be a solution. There has to be no time conflicts of the meetings. So he's making the argument that there are no time conflicts of the meetings. And I think I have the argument. I don't have it. I have to argue it. So the idea is, so remember, M prime is the meeting in the original S that had the earliest the earliest ending time. What do you know about M's ending time? How does M's ending time compare to M prime's ending time? Yeah.
It's what he was saying, that it's either the same as or earlier than.
Right. It has to end at the same time as M prime or earlier, which tells you that if M prime did not conflict with anything else in S, neither can M, because M ends even earlier than M prime did. All the other meetings in S start after M prime ends. So they also have to all start after N ends. So it's safe to replace M prime with M. And keep in mind, we're not doing this, this isn't something you do in the algorithm. This is how you argue the algorithm is correct. It's the argument that that there is always going to be an optimal solution that contains the greedy choice. That justifies the greedy choice. That's how you justify the greedy choice. Yeah?
How do you know again that M doesn't conflict with any other meeting?
Okay. M has the earliest ending time. Okay? So how could there, what would it, how do we know that there's no meeting that, it doesn't say anything about when M starts. So how do we know that all the other things in the set, I'm going to have to, let's draw a picture here. Okay, so we got a bunch of meetings to schedule in some interval, which I'll draw here. And let's say the meeting that has the earliest ending time is M. So this is M right here. I claim that all the other meetings in the set S here start after M ends. How do we know that? That was his question. How do we know there are no meetings that start before M? Yeah.
If you assumed S was an optimal solution to begin with, so there can't be any conflicting meetings.
Where there can't, right, there can't be any conflicting meetings. So if there's some meeting that starts before M starts, or, you know, it would have to start here. And it couldn't end before M. We know it doesn't end before M because the assumption is M ends first. So it's going to have to end somewhere down here. It's going to have to conflict with M. If it starts before M ends, and it ends after M ends, there's going to be an overlap, and that's not allowed. Okay? And then the in pictures, the rest of the thing is, so there are going to be more meetings. Say this is solution S. There are going to be more meetings scheduled. And then we got this meeting M prime. So this solution does not contain our greedy choice, which is M prime. M prime has the earliest ending time of all. So maybe M time looks like this. This is M prime. So do you see why it's safe to kick out M and stick in M prime? If M did not, we know M didn't conflict with any of the other meetings in this set. There's no way M prime is going to conflict because it stops even earlier. And so we've transformed it into a set that is an optimal solution and contains a greedy choice. And the full proof of the correctness is an inductive proof on the length of the solution. The idea being, okay, given that the set contains, there is an optimal solution that contains M prime, okay, then you reduce the problem, make another greedy choice, and you make exactly the same argument about that greedy choice. It has to be in an optimal solution for the rest of the problem. And you continue in that fashion. So the inductive part of the argument, fortunately, is the same all the time. You know, it's just basically show that the first greedy choice works, show that the second greedy choice works, and so on. How these proofs differ is in how you argue that the substitution works. All right, so there was that. Let's take a break and then we'll continue, look at some other examples. All right, as I mentioned, this meeting scheduling problem is an example of an optimization problem. It's an optimization problem that can be solved with a greedy algorithm. And the way optimization problem works are you have a set of choices to make subject to constraints. In our case, we've got to choose meetings. They can't overlap. And your goal is to find an optimal set of choices where there's some metric that defines optimal. In our case, we want the largest possible set of non-overlapping meetings. And we'll look at other examples of optimization problems as we go along. They're very common. Like, for example, a famous optimization problem is if you're UPS and you want to deliver your packages for the day and end up back when you started, what's the way that is the fastest or that uses the less gas or causes the fewest accidents, things like that. So these problems occur in practice. For the time being, we're interested in optimization problems that exhibit what's called the optimal substructure property. So you got the fancy definition here. It says it exhibits optimal substructure if every optimal solution contains within it optimal solutions to each of its subproblems. So what that means is probably easier to show the picture. You've got, this is the meeting problem, and those are our 4 meetings that we scheduled. So that's the optimal solution to the original problem. Now, suppose you change the problem by just throwing this meeting out and throwing out the time it occupies. So we've produced a subproblem by eliminating one of the choices. So now, let's go back to the original problem where there are lots of meetings to schedule, but the room is only available for this period of time. What is the optimal set of meetings for this problem? These 3. That's what I mean by the optimal solution contains within it optimal solutions to the simpler problems you can generate from. Okay? Because there's some problems that don't exhibit that. Yeah.
So if it has the optimal substructure property, when you're using like a proof to show that it's the most optimal, will always have an induction.
Okay, so let me take that apart. To solve problems using a greedy algorithm, the problem needs to have the optimal substructure property. And then that's where the induction comes from. That's why the induction works. Right? So there are 4 subproblems to consider. And again, if we take out that if we simplify the problem that way, the first, third, and fourth are the optimal solution. Okay? And again, I'm talking about the optimal. You have to consider all the meetings from the original set. But you're not going to find a better solution among those meetings for this subproblem than those 3 right there. So anyway, optimal substructure is good. It doesn't always exist. Sometimes those problems are harder. If you don't have optimal substructure, you can't take a greedy approach. But not all such optimization problems can be solved. And again, this is sort of the high-level description. You survey the choices and efficiently pick one. So you don't take exponential time to make the choice. That's sort of abusing the notion of a greedy algorithm. You do something that's fast. You do something fast, find the choice. You eliminate the conflicting choices, solve the reduced problem, and you keep doing that. And there's never a need to reconsider, back up, try a different way. And I've already shown you that proofs of correctness involve showing how to transform optimal solutions that don't have the greedy choice into one that does. And that would fit into an inductive template that lets you really prove it formally, but we're just going to worry about justifying the greedy choice. Okay, this, I've already sort of mentioned we won't consider this in any detail, but these are other variants that are optimization problems. Maximize the amount of time the room is in use, maximize the number of people, maybe meetings have different values, more important people get priority. So you can imagine all kinds of variants. But here's one we will consider. Making change. So let's say you go, you're a cashier and someone gives you $1 and you got to give them 24 cents in change. Most cashiers that do that in this country follow the same algorithm, a greedy algorithm to make change. What is that algorithm? First of all, what are they trying to optimize? Yeah.
Trying to give the fewest coins back.
Right, so their goal is to give the fewest coins back, assuming they have a supply of all the coins. So what's the algorithm to make any amount of change with the fewest amount of coins? Yeah.
Take out the largest coin first.
Okay, so you always choose the largest value coin that you can. So if you want to make 24 cents in change, the largest thing you can use is 10 cents, a dime. So you use that, and then you simplify the problem to making change for 14 cents. Dime still works, so you pick a dime. Now you got to make change for 4 cents, and then you use 4 pennies. So 6 coins. That's the fewest coins you can give change with. Right, so that's a greedy algorithm. Okay, so there we have an example. So for 30 cents, you use a quarter and a nickel. For 12 cents, you use a dime and 2 pennies. 55 cents, assuming you don't have a half dollar, you use 2 quarters and a nickel. Now, that's a greedy algorithm. What if Congress gets rid of the nickel? We're more likely to get rid of the penny, but suppose they got rid of the nickel. Would there still be a greedy algorithm? Or at least would this greedy choice work? What would it be? Yeah?
Fail on 30 cents.
Fail on 30 cents? Okay. How would it fail on 30 cents? Okay, let's think about it. So if you make 30 cents in change, what would the greedy algorithm say to do? Again, you can't use a nickel. You give back a quarter and 5 pennies, 6 coins. But what would be the optimal solution? 3 dimes. So if we live in that world, it suddenly becomes harder to make change. Greedy, and the reason is because that greedy choice doesn't work anymore. So, I guess it would fail here. It would work okay here. What about here? Yeah, here you get 2 quarters and then 5 pennies. I think that's the best you could do. So we could worry about it, and we could try to characterize situations in which it works. Another thing we could do is we could try to go back to the original problem and make the argument and try to prove that choice is correct. It's a little bit tedious because of the basically every coin's a special case. So I'm not going to try to do that. But we sort of all intuitively understand that greedy algorithm, or most of us do, that algorithm is used most of the time and that it seems to work. But it's eye-opening to realize that it's not guaranteed. It just depends on what coins you have. Okay? Now let's look at another example, a couple examples of greedy algorithms. This is a graph problem. It's called the minimum spanning tree problem. And a minimum spanning tree, you're given an undirected, connected, weighted graph, like this one here. So everything's connected together. There are no islands. It's undirected, and you've got weights. And your goal is to find a tree, which just basically means a subset of the edges that don't form a cycle, that connects all the vertices together, that has lowest weight. So one way to think about it is, imagine you have a bunch of electrical outlets in a building, and you want to hook them all together in some fashion. You just need electrical continuity between all the outlets. And it doesn't matter to you if they get strung together all in a line, or whether there's one outlet in the middle and there are wires going out to all the other outlets, although that would violate code, but not for the proper purposes of our problem. And you want to use the least copper possible. So you're not trying to find shortest path from any start vertex to everything else. You're just trying to connect everything together as cheaply as possible. That's the minimum spanning tree problem. So can you see the solution? What's a solution to this? Yeah.
A to C, C to D, C to F.
Okay, so you're saying A to C,
Yeah.
C to D, and then what?
C to F, and then F to E.
C to F, F to E, you got to hook in B.
Wait, yeah, B. D to B, I guess.
B to B. Yeah, I think that works. I think I have a highlight here too. Yeah, I think that's what pretty much what you said. So that is the shortest path tree. And with not the shortest path tree, the minimum spanning tree. And notice there's no start vertex. You don't say where you're starting. You're just trying to hook them all together. What makes it a tree is there are no cycles. Obviously, if you have a cycle, you're wasting copper, say, if you're hooking things together. Sometimes it's going to be the case that, say, the minimum spanning tree rooted at A turns out to be the same, the shortest path tree rooted at A turns out to be the same as the minimum spanning tree, but not always. The minimum spanning tree can have a lower total weight than a shortest path tree, simply because it's the minimum spanning tree. All right, so that's the thing. Total cost of 13. So I'm going to show you two different greedy algorithms for solving the problem. We won't worry about proving correctness until after spring break, if we do it then at all. First one is just repeatedly choose the lightest edge that does not create a cycle. Okay? Pretty simple. You just survey all the edges. Essentially, you could start by sorting the edges into order of weight. And then at each step, you choose the lightest edge that does not create a cycle. So let's try that out. What would be the initial greedy choice? A to C. Okay? And then, let's see, we got this edge here, C to D. That's 2. And E to F. So I just chose this one first, just for variety. So they don't have to be connected at all. They eventually will be. What will we choose next? C to D is the lightest that does not form a cycle. Now let's say this A to D is the lightest edge, but forms a cycle. So to use this algorithm, we need some efficient way to detect that edges form a cycle. Yeah?
Just check if both edges are already connected.
Well, okay, you can't check that both edges are already connected because it would rule out this edge from C to F. Right? Your idea would work if you were growing the tree continuously, but we're sort of picking it up here and there. So we'll see a special data structure for this later. Okay, so what does come next if we don't do A to D? All these edges of length 4 are good. They don't form cycles, so one of them will come next. Let's say that one. And then all that's left is that one. So that gives us a solution. So turns out that's a greedy algorithm. Now, I sort of go back and forth on the answer to this next question. Is Dijkstra's algorithm a greedy algorithm? What do you think? It sort of seems like one. You're looking at a bunch of choices and making one, but you later can go back. You find you add an edge to the tree, and you can later change your mind and add a different one. You find it when you find the shortest path. So it has a lot of the feel of a greedy algorithm, but technically maybe it's not. Okay, here's Prim's algorithm. It's a lot like Dijkstra's algorithm. We're going to grow the tree. We're going to arbitrarily pick a starting vertex, and at any point we're going to have the vertices. Well, there's our starting point. So at any given time, we're going to pick the lightest vertex that goes from a yellow vertex, the lightest edge that goes from a yellow vertex to a white one. That goes from the vertices that we've seen so far to one on the fringe. So which would happen first? A to C. Now there are two, those are connected. So which would we do next? C to D would come. And now we want, Kruskal's would do this one, but this isn't Kruskal's algorithm. So we'd pick one of these edges of length 4. And then we would pick this one of length 4, and finally we would pick that one. So when I show you the code after spring break, you'll see that it looks a lot like Dijkstra's algorithm, except there's no it uses a priority queue, as you might expect. It's just the weights are computed differently. Okay, so that's Prim's algorithm. Okay? Here's one from a programming contest site, Top Coder. Gold mines. So imagine you have 2 gold mines. Each, they're up to 6 deposits in each mine that you could explore in, and their probabilities. So mine 1, there is no chance that there are no deposits. There's a 30% chance that there's exactly 1 deposit. There's a 30% chance that there's exactly 2 deposits, and so on. So in that mine, you've either got 1, 2, or 3 deposits. Mine 2 is different. There's a chance that you've got 0 deposits, there's a chance you've got 6 deposits, and everything in between. So you've got the probabilities of those occur. So this is a very contrived problem compared to what we just looked at. You can employ up to 6 miners per mine, and you're trying to optimize your profit. And here's how you optimize the profit. This is how you define your profit. So you don't know going in how many deposits are going to be. If it turns out that you hire fewer miners than there are deposits, your profit is going to be $60 per miner. If you happen to hire exactly the right number of miners, your profit is $50 per miner. And if you hire too many miners, it's going to be $50 per deposit minus $20 per excess miner. And so that's sort of a lot to get your head around. But just look at it in this case. Suppose you decide to hire 1 miner. What's your expected profit? So the idea is 30% of the time you'll make $50 of profit. Now why is that? You hire exactly 1 miner. Where does that 30% of $50 come from? Yeah?
There's this 30% chance that there's only 1 deposit.
Right. There's a 30% chance you'll be in this situation. You'll have exactly the right number of miners. So you're in this case, so you get $50. 30% of the time you make $50. We left this out because there's no chance there'll be 0 deposits. Okay? What about 30% of $60? Where'd that come from? Okay, so if you're in this situation, you have a 30% chance of being in the situation. You're going to have fewer miners than you are deposits. So you're in this case, this case where you make $60 per $60 per miner. 1 miner, so that's $60. So 30% chance of making $60. This next one here is the same, except it's wrong. I'm going to say 40% right there. I edited this last night, and that's what I get for doing that. Mine 2, there's going to be a bunch of cases. 20% of the time there'll be no deposits, but we hired 1 miner, so we get $50 per deposit, but there are no deposits, minus $20 per excess miner, so we lose $20 in that case. And it proceeds on from there. So the question is, given this table here, and how many miners should you hire to maximize profit? Or I guess the way the problem is stated, given a number of miners to hire, what's your profit going to be? How do you allocate miners to mines? And I'll stipulate that there's a way to make the greedy choice. Got an idea?
I'd just say you always try to opt for fewer miners.
Always try to what?
Opt for fewer miners.
Well, so, to take that to extreme, opting for fewer miners, you could hire no miners. You'll get no profit. So you don't run any risk of losing money. But in either of these cases, you're better off hiring at least 1. But the problem actually isn't how many should you hire. It's assuming you're going to hire in, how should you allocate them to mines? Yeah.
My initial thinking would be to sort of approach it like the scheduling problem, where you take a look at, with only one minor, what would be the most optimal place to put them in that case, and then add in another. But I'd also have to consider what happens when you now change a previous
Okay.
situation.
All right. So here's a situation that would make it difficult to use a greedy algorithm. Suppose the solution we're going to look at is going to work where we're going to look at the data. We're going to say, okay, the first minor should go in mine 1, let's say. We're going to figure out where we should put the first minor. And then we're going to say the second minor should go in mine 2. And then maybe the third and fourth minor should go in mine 1 again. But what would shoot us down is if it were the case that we would make a decision, we would say, okay, if we have one minor, we'll put them in mine 1. The second minor will go to mine 2. The third and fourth minors will go to mine 1. But if there's a fifth minor, we're going to take one of those minors out of mine 1 and put it in mine 2 along with the new minor. So we've had to undo a previous choice. That would say, that we wouldn't be able to use a greedy algorithm in that case, if you ever had to backtrack on the choice. It turns out that you don't have to do that if you look at it the right way. Anybody have a specific recommendation for a greedy choice? Because it's not always obvious, and it's certainly not obvious in this case. Okay, you have to, in this case, you need to do a little pre-processing. So that's the original data up there. So our question is, you're given n, and you're supposed to decide how to allocate them to mines. So that's our original data up there. This is the profit or loss corresponding to each number of minors. So for example, if you put one minor into mine 1, your profit's $57. That's what we computed on the previous slide. And mine 2, it was $44 if you have one minor. On the other hand, if you have 2 minors, your profit in mine 1 is going to be 87. 3 is still going to be 87, and so on. And similarly for mine 2. So the first step is just to compute for any given number of minors, what's the profit or loss for that number of minors. And then see if you figure out where this table came from. Yeah.
It's the amount of profit from the previous minor, like, that you gained.
Okay.
It's the amount of profit you gained by adding another minor.
Okay. So if you have no minors, you're making no money. If you add one minor, you're making $57 more than you were before. Okay? If you add 2 minors, you're making an additional $30 than you were before. If you have 3 minors, you're not making any more money than you were before. If you add another minor, you're losing $20, and so on. And you see the same thing for mine 2. Now, do you notice any pattern to those numbers? They're decreasing. And it turns out if you think about the problem long enough, the way it's set up, you can convince yourself that these numbers decrease, or at least don't increase. It's a non-increasing sequence. So, given that, now that I've done this pre-processing for you, how would you decide where to put each subsequent minor? Where would you put the first minor? If you've got one minor to use, where do you put it? Mine 1, because that buys you the most, $57. Now that's out of the equation. Where should the second minor? If you have 2 minors, where would you put the second one? Down here. Then the third one would go here, the fourth one would go here. Where would the fifth one go? Right there, and so on. So this is, I'm not saying this is an easy problem. It's just typical of a greedy algorithm, in that sometimes it takes a little bit of pre-processing. Now what if we change the problem so that there are more than 6 mines? Not more than 6 mines, more than 6 deposits. Suppose there could be 1,000 deposits. Would this same approach still work? Sure. What if there's more than 2 mines? What if there could be 10,000 mines? Yeah, that would still work. you'd have to think about when you implement the problem, you have to have some efficient way of figuring out which, which mine had the most profit. So you'd have to organize the data into a list and keep it sorted or something. You have to think about that to make it efficient. When it's small like this, you can just eyeball it. If it's large, you've got to be sure to use the right data structures to make the greedy decision fast. But it scales up. And this just summarizes what we just saw. Okay, so the caddis problem that you're doing after spring break is a greedy algorithm. The way you make the greedy choice isn't going to be as difficult as this. It's not going to be as hard to figure out a greedy choice, but you are going to have to figure out how to make a greedy choice. I want to finish with one last famous example of a greedy choice algorithm, or of an optimization problem called the knapsack problem. And it's this. You have a thief that has a knapsack that can carry at most W pounds. The items in the table are available in limitless quantities. So there are three things a thief can steal: a type A, a type B, or a type C. And each one has a weight and a value. And the question is, which should he steal? He wants to carry away, he can only carry a limited amount, but he wants the most valuable. This is a generalization of that coin changing problem. So, the question is, what item should he take? So suppose the thief can carry 10 pounds. What should he take? An A and a C? That gives him $17. Okay. What about 12 pounds? What would you take? CCC gives you 12, but what about, well, actually you could do 4 C's, which would be 16, but you could take 3 B's, which is 21. What about A? Would it pay to take an A? Don't think so. So BBB is what you do in that case. What about with 9? Three C's would give you 12. Let's see. But 2 B's, even though you don't use a full capacity, it's better to take 2 B's. Okay? So that's the knapsack problem. Can you think of a greedy choice? Yeah.
The object with the most value to weight density. So like the most value divided by weight, whatever has the highest.
Okay, so you take. So let's nail that down. You've got some capacity left in your pack. So first of all, it's got to be an item that can fit in your pack. And so you take all the items that can fit in your pack and take the one that has the most, the ratio of weight to value, or value to weight. Yeah, value divided by weight. Okay, does that work? No. What's a counterexample? Let's. Okay, number 2. Let's see what number 2 is. So number 2, you took 3 B's, and their ratio is 7/4. Okay, so how does it not work? Okay, A has a better ratio, but you didn't take A. Thanks. Okay, any other ideas? Mm-hmm.
I guess you could make like a table of compound items that combine different items and take the ratios and all of them. Like anything up to like.
Okay, so he's suggesting maybe we make consider all ways to combine items and compute their ratios. But you got to be careful because you can end up with an exponentially large table. Because there are lots of ways to combine these things in different quantities, and then you have an exponential greedy choice algorithm, which isn't going to be practical. Yeah?
So you take the greatest common divisor with W and the first weight, and then with a leftover, or you keep subtracting it and then go to the weight that's closest to it.
Okay. I won't explore that in detail because no one has ever found a greedy algorithm for this. Okay? This problem is a very famous problem. It's an NP-complete problem. We'll study that in April. But the bottom line is that A, no one's ever found an efficient, greedy solution for it, and B, people in the know really doubt that there is one. It hasn't been proven that there is one, but if you found one that worked in polynomial time, even if the polynomial was huge, you would have made a major breakthrough. So just be aware that problems like this can look fairly simple and easy to attack. It can be deceptive. It's hard to tell whether you'd be able to solve something with a greedy algorithm. So I want you to stay healthy over spring break as you travel. Be sure to wash your hands, because I want to see everybody back here in 12 days.